It is only to be understood. Now it's time to understand more so that we may fear less. Good afternoon to all. Today we are gathered here for the International Webinar Series Vykhari 2021 as part of the Diamond Jubilee celebration of our college. Vykhari, which means dissemination of knowledge through words, was officially inaugurated on 14 September 2021 by Honorable Vice Chancellor of Mahatma Gandhi University, Kottayam. And the Department of Chemistry presents lecture on topic New Generation Catalysts for Water Splitting. For that, we have our Honorable Resource Person, Dr. Prashant Wilfred Meneses, Research Associate at Technical University, Berlin. A day without prayer is a day without blessing, and a life without prayer is a life without power. Let's start with a silent prayer. Now I invite Ms. Mariam Elsa Thomas of third year chemistry for delivering welcome speech.
A warm good afternoon to one gathered here. Today's international web conducted by Department of Chemistry on the topic New Generation Catalyst for Water Splitting as part of our international webinar series by KP 2021. And taking this auspicious opportunity to welcome our honorable researcher, Mr. Prashant Wilfred Meneses, to this international webinar series. Welcome to this web. Dr. Prashant is currently a professor in organic materials for Electrolytic Cell at the Department of Chemistry in Technical University, Berlin, Professor of Materials and Energy in Germany. His research focuses on the design and structural understanding of novel and conventional chemistry and heterogeneous analysis, especially in the area of redox oxygen catalysis, electrocatalytic water split, as well as electrochemical reaction.
Excuse me, Mariam. Your voice is breaking. Can you please move it forward? Move to the
Sorry. I feel that the connection is a bit poor. Anu, did you say something? I'm sorry, I cannot hear anything. Me, and also thank you Amalumul and also Miriam for nice introduction. Okay, so I will just share my slides. Please let me know whether you can see the slides properly. Can you see it?
Yes, sir.
All right. Okay. Okay. Today I will speak about new generation catalyst for water splitting. Before going to the topic, I would like to show you some glimpse of Berlin. As you could see, Berlin is somewhere situated in this area, which is north of Europe, and Berlin is somewhere northeast of Europe. So there are some nice monuments in Berlin. For example, as you could see, this is a city view, which is situated at Alexanderplatz, and then you have very famous Berlin Wall, which separates east from west of Berlin. Then we also have Brandenburger Gate, which is a very popular monument. And also Berlin is known for its shopping streets. So this is one of the top view of Friedrichstraße, where one could come and shop as much as they want if they have money, of course. Berlin is not only known for monuments, but also it's a nice party place. As you could see, that a lot of students come to Berlin just to party. Yeah. Anyway, so in Berlin we have 4 big universities. For example, we have a Technical University of Berlin, and then we have Freie University, and then there is one Humboldt University. A little outskirts of Berlin, we also have Potsdam University. As you could see from the numbers, the universities are quite large. And I would like to show you the campus map of TU Berlin, where I work and my group is working. So this is the main street in Berlin, and this university is in the heart of Berlin. So this is the chemistry department, which looks pretty old, but inside you could see that it's very nice. Nevertheless, I will not show the pictures what is inside. However, I work in or my group works in the second floor of this building. All right, so now let's go to the topic. So I have outlined my the talk into 4 different parts. For example, first I would speak about some basics of water splitting. Then I will give you a short overview on photocatalytic water splitting, and then I will come to the electrocatalytic water splitting, where I would explain you the process with some examples. And finally, I will tell you, or I will explain you a short summary and a short outlook. Okay, so why we are doing this research? As you know that the energy demand is rising day by day. As you could see from this chart, that the primary sources of energy in late 1800 to 1950 were especially wood and coal. And then during this particular time, oil and nuclear power came, as well as natural gas was rising. So, but today we have to rely on renewable energy. What are the advantages of using renewable energy? As I have pointed out, 3 important benefits. One is that you do not emit any greenhouse gases such as carbon dioxide. So that means you don't have to rely on fossil fuel anymore. And this is also important that we are reducing the air pollution, which is the problem at the moment. And also, we are diversifying the energy supply and reducing the dependence on imported fuels. So as I said, we don't have to really rely on the imported fuels anymore. We could use our renewable energy to compensate our energy demand. Okay, so I would just show you what is the situation in Germany. For example, Germany needs almost 277 terawatt net power generation, or let's say almost, yeah, this much of energy is required to compensate. So most of the energies now you see are coming from renewables. And of course, we also have about 24% of lignite and hard coal, as well as some amount of natural gas and nuclear. However, if you see this renewable energy, which is close to 37% at this point of time, and which is expected to reach about 50% this year, and which has a large amount of energy generated from wind power. Then we also have biomass and solar power. Also, we use hydropower to compensate the energy. But now I would like to show you a scenario where if you look at the summer of 2017, the data is pretty old, but it's interesting to see how energy demand rises. For example, this is the energy demand, what is required in Germany, and how we compensate with renewables. That means solar and wind energy. As you would see that in winter, the energy demand remains the same, but we have wind power, but in Germany, we have less solar energy in winter. So the difference is pretty high. Therefore, we need an alternative energy source. What could be that? One of the best way to have alternative energy is from hydrogen. So this is much better than fossil fuels. So what you do, if you take fossil fuels, you generate energy, but you get unwanted carbon dioxide. However, if you take hydrogen, you are producing energy, but the byproduct is always water. So hydrogen is not only important in industrial conditions or industrial reactant, but also it could be used as a fertilizer, also in numerous reactions in the laboratories. I think it was in June last year, Germany decided to spend almost 9 billions of euros for hydrogen economy to produce and to deliver hydrogen. The reason they cite was most hydrogen used today is produced by reforming natural gas, which releases a lot of carbon dioxide. However, if you use green hydrogen, which is extracted, if you extract it from water electrolysis, for example, which is very good. However, it is still very energy intensive process. So we need to look for some further research to make it less energy intensive. So before going to what is water splitting, I want to show you what are the available platforms to have water splitting. For example, one could use thermal energy or biochemical energy, or couple them together as thermal or biochemical, or one could use electrical and thermal and couple them as well. Also, you could use photonic energy, which is from sunlight. However, at this moment, the hot topics are use of electrocatalyst, which is from electrocatalysis, photocatalysis, as well as the coupling of those as photoelectrocatalysis, which are mentioned here. Okay, to do these reactions, we need a catalyst, of course, and you know from your basic classes or chemistry classes that a catalyst is a substance that increases the rate of the chemical reaction, but without undergoing any permanent chemical change. This is the energy diagram. You have your reactants, and you want to have your products, and you have your activation barrier. So if you use a catalyst, you are decreasing your activation energy. That means lower the activation energy, faster the reaction of a catalyst, and which also reduces the cost and accelerates the reaction. So now I would be using two terms in this talk, which is a photocatalyst and electrocatalyst. So what exactly they mean? A material which absorbs light to bring it to a higher energy level and provide such energy to reacting substance to make a chemical reaction occur. That means you are giving your energy, such as in the form of sunlight, to make the reaction occur. Other way around is an electrocatalyst, where a catalyst that participates in electrochemical reaction. It could be an anode or a cathode, which in general is an electrode which participates in the reaction. So from the basic definition, you know that catalyst should not undergo any chemical reaction during your catalytic process. However, most of the heterogeneous catalysts change during the catalysis, which is termed as pre-catalyst, which I will be explaining in my talk later on. Let's talk about photocatalytic water splitting. So now if you see, what is water splitting? Water splitting is nothing but you split water into hydrogen and oxygen. And for photocatalytic water splitting, what you need is a photocatalyst and just sunlight. This looks very simple from the equation, as well as what is represented here, sunlight and photocatalyst. Is it that simple? One should look at it in a very detailed way. So just look at a semiconductor. So you have, if you know from your classes that if you have a semiconductor, you have a valence band and a conduction band, which is separated by a band gap. So let's imagine that we are illuminating light. When the wavelength of light is larger than the band gap, you are exciting the electron from your valence band to the conduction band. So you are creating an electron hole pair, actually. So here you have hole and here you have the electron. What happens then, that the hole will move to the surface so as to oxidize water in the form of oxygen evolution reaction. Similarly, the electron will move to the surface and reduce protons in the water to form hydrogen. So this is the hydrogen evolution reaction, and this is the oxygen evolution reaction, where you use holes, and here you use electrons. But there's a big problem here. When the electron hops from valence band to conduction band, it always wants to come back to valence band. So the recombination rates for these reactions are very, very high. Therefore, what could be done? One could use something like co-catalyst, which can trap the electron the moment it goes to conduction band, and then it can produce hydrogen at one end, and the other end it can take out the hole and somehow makes this oxygen evolution feasible, so that we don't have any recombination. Now the question is, does such a catalyst exist? So you can see the band structure of the semiconductors. This is the band gap. What you see here, you see that most of the catalysts or most of the materials, they do not have suitable band gap to oxidize water or reduce proton at the same time. What one could do is that you can make half reaction. That means you can produce hydrogen, which is what we want, and also the oxygen evolution reaction, which is an important reaction to compensate the other half reaction. How we can do that? So you hop the electron from your valence band to the conduction band, and immediately you can quench the hole by the donor atom, which sacrifices the electron and quenches it. So you can use the electron to make only hydrogen, no oxygen. Similarly, you can do the other way around. You can take an acceptor molecule, take the electron immediately, and use the hole to produce oxygen. Yeah, this is very simple. So you can do this in both ways. So there are some catalysts which are already prominent in this area. For example, cadmium selenide, which has a band gap of 1.7, which is very suitable for hydrogen evolution reaction. Also, cadmium sulfide and carbon nitride, which is a metal-free catalyst, which is very popular nowadays. Nevertheless, what I want to show is that we also worked in some of these reactions where, as I said, we quench the hole and produce only hydrogen. So this is the carbon nitride as shown here, which is yellow in color. The band gap of this material is almost 2.7 volt. And you see this is the band gap, and the moment the electron goes, we could use a co-catalyst, which I showed in the previous slide. We use something like a nickel phosphide catalyst or something like nickel catalyst to produce hydrogen. Okay, maybe I can show you a video where how we can produce hydrogen from photocatalysis. As you could see that we have kept our carbon nitride material in this vessel or in this reactor, and this is the simulated sunlight which we focus on the material, and your material is getting stirred at the same time so that it can have a maximum exposure to the sunlight or simulated sunlight. And what would you see here is the generation of hydrogen. Slowly you can see these bubbles, and they will be collected on the top of the reactor. As you could see here, over here, and those and the collected hydrogen can be taken out and used in a motor as a coupled with a fuel cell to generate electricity, which you could see here at the, yeah, this is the motor here, and then you could see a fan is turning very fast. So this works perfectly fine. So hydrogen is very important, and we could produce it in a lab scale. We also show that we could also make hydrogen in a very large scale. So this is the plates which we deposit our carbon nitride, and this is on the rooftop of our chemistry building, and we put it to a real sunlight conditions. Yeah, and the area is almost 1 meter square, and we could produce large amount of hydrogen, which is almost 80 ml per hour. This is also, you can see from the graph, but you see also some amount of decrease because in the night we don't have sunlight, so you also have a decrease in your hydrogen production. Okay, so this is what I wanted to give you a brief idea about how photocatalysis work. And the other process which is very interesting is also called electrocatalytic water splitting. So here I would like to explain you with a couple of examples. So what is electrocatalytic water splitting? So this is an electrocatalytic process. So you have a typical electrolytic cell. Again, this you probably have already known in your basic chemistry classes. You have an anode and cathode. What happens in your anode is oxidation at your, and what happens in your cathode is a reduction. So you are using a material as an electrode in this place or over this, and what we can produce if you put water is oxygen evolution. This is oxidation process, and hydrogen evolution at the reduction cell. Okay, so now how simple is this? So the problem here is the oxygen evolution reaction, because which determines how much hydrogen can be produced, and it also determines the overall energetic efficiency of the reaction. So you could see this is the equation for oxygen evolution reaction, which is a very complicated 4-step reaction. This because it involves 4 proton, 4 electron transfers. So what you do, you take water and it forms OH, and then it takes one more proton and one more electron, and then you have O adsorbed, and then it couple to get OOH, and finally O2 is released. This is some of the complicated processes, but what you want to know is that this step, which is the formation of OOH adsorbed on the surface, is the most difficult step, and this is called the rate determining step. Now, most of the noble metals work efficiently for this reaction, such as ruthenium and platinum or iridium. However, the transition metals, which are very cheap, are not behaving in a reasonable way, or let's say they're economically they're not feasible. Similarly, if you look at the other reaction in the same electrolytic cell, you have hydrogen evolution reaction. Here, the process is quite simple. Let's say only 2 electron transfer reaction, and what you need is the formation of adsorbed hydrogen, which couples with the next proton to form hydrogen. However, this reaction is completely determined by how efficient this reaction is. So this is an important reaction to get better energetic efficiencies. Okay, the dream, of course, always to couple this reaction into an electrolyzer. So what you can do, you can make a film at the anodic cell or anodic compartment or a cathodic compartment. You have your water or in acidic, alkaline, or neutral solution, and what you want to produce is hydrogen, oxygen at the same time. Okay, now the question will arise, does this technology already exist? Of course, such a technology existing since a long time. So what we have is something called alkaline electrolysis, or this is for alkaline media, and something like proton exchange membrane electrolysis. In proton exchange membrane electrolysis, what industry uses is mostly noble metals, which is iridium and platinum. And for alkaline electrolysis, the industry uses cheaper metals such as cobalt, iron, nickel, or nickel carbide, for instance. And how or why we should look at these parameters, as you could see that the current density, which I will explain a bit later, for this reaction for alkaline electrolysis is pretty low, whereas PM cells, which is a bit larger. And this is an important factor which determines the efficiency. This is the cell voltage, which is also similar for both electrolyzers, but important thing is the stack lifetime and the system lifetime. We would like to have our electrolyzer running for some years, like say 20 to 30 years, because you need energy constantly, and you have to compensate this energy through better stack lifetime or the system lifetime. Okay, so now this motivates us to make certain materials for alkaline electrolysis, where we can bring this factor much down, or much we can decrease it much further and increase this factor much higher, and also let's say increase these factors as well. Okay, so in my group, what we are doing is we are determining new generation catalyst. So we use several synthetic methods, starting from solid state, hydrothermal, molecularly derived, and so on, to get nanoparticles or sometimes microparticles, and we understand the structural and chemical and electronic properties of those materials, And once we have this, we make nice films of those materials to use as electrodes by various techniques. I will not go into details of these techniques, but what is important is the catalytic activity and durability, where we use for different catalytic applications, starting from chemical, photochemical, electrochemical, or photoelectrochemical. And then what is also interesting, what I told you in the beginning, we look at the catalyst, whether it's changing or it remains as it is. So this can be done only through better to be done via in situ or in situ methods, or even we can also try to see the surface by ex situ method. Then we try to have a structure activity relationship, how the structure is affecting the activity, and more mechanistic insight by delivering a reaction mechanism. Finally, when we make all this, we have to use it. So we tune the structure of this catalyst so that we can optimize them for practical applications. Okay, so now let's imagine that you made a nice material. So how to check the activity, whether it's good or bad? So first, what you need is a substrate that is that we use commercially available indium tin oxide or fluorine doped tin oxide or nickel foam, which are highly porous. These are the scanning electron microscopy pictures. As you can see, this electrode is very porous, this is not, but this is it's a very traditional electrode, very transparent, conductive, and you can deposit any material on it very easily. And this is also stable in very large potential range. Similarly, this substrate is also which has a 3D porous and high surface area. It also has improved mass transfer. That means when you produce hydrogen and oxygen, it should not remain on top of it, so that it hinders the other active sites. Also, this is cheap and inert, just like this. So, okay, now we have now we bought our substrate. So how do we deposit? I will show you one method how to deposit. So what you could do, you can take your particles, you can disperse it in, let's say, acetone, and you can add some iodine, which forms a keto-enol tautomerism, and which produces free protons. These protons would be absorbed on the particle, and if you apply a potential, they will be migrated towards either anode or cathode, depending on what potential you apply. And then you get very nice films as shown here. This is, I think it's a film for a cobalt oxide. As you could see, you can get a very nice, highly dispersed film. And this is the same film on nickel foam. And this is a 3D porous material. So you could see that you still see the pores. And this is the flat surface. Okay, so now we made the films. Now we have to check whether it's active or not active, or whether it can produce any hydrogen or it is inactive for oxygen evolution. So what do? We have an electrolytic cell, which contains a working electrode. Here you connect your electrode, what you made already, and you have a counter electrode to compensate the work electrode, and then you have a reference electrode, which references between the working electrode and counter electrode. Here, it doesn't matter what counter electrode you use. People use graphite or platinum. However, you can also construct an electrolyzer by using a 2-electrode cell. You can use your electrode which you made, and then you can use just a counter electrode. Or you can also use the same material here, which is called bifunctional electrodes. Nevertheless, there are some important factors which one could think about it. Now I'll tell you what are these important factors. So the thermodynamic potential to form oxygen evolution is about 1.23 volts. So whatever potential you apply larger than this is called over-potential. Similarly, the thermodynamic potential for hydrogen evolution is almost zero. So whatever what potential you apply here in this cathodic direction, which is called also an over-potential for hydrogen evolution reaction. So this is a very important factor, and also the stability is also a very important factor for this kind of reaction. There are some other parameters which are also very important, such as Tuffle slopes, which determine the kinetics. There are some factors such as electrochemical surface area, how much available active sites on the surface. You have turnover frequency, which will tell you how fast the reaction is, and then you have this mass and specific activities. How much loading of the catalyst is required, and something about charge transfer, which is done by impedance spectroscopy, also Faraday efficiency, which determines how much oxygen and hydrogen you produce. I will not go to any of these details because which are probably not important at this point of time. What I will stick to is O potential and stability, which are the fundamental and very important parameter to have such a reaction. Okay, so I will simplify the whole scenario with some examples. So this is one of the example, which is called Boro phosphate as a new generation catalyst. So Boro phosphates are a class of materials which are made up of borate and phosphate tetrahedra. What actually you could take phosphorus oxide, boron oxide, and with some metal oxide. So how do they look? Is shown here. They're very nice. You can see some different architecture which can form oligomers, the rings, chains, layers, and framework. They can be further connected with the metal octahedra to form a three-dimensional network. Just simply to show you that how the whole thing works, you can increase the phosphorus ratio and you can form different architectures or different dimensionalities. And if you use the borate or let's say boron ratio, you could still form, let's say, only chain structure, which is probably not important at this point of time. What is important is what we are doing at the moment. So we cyclosynthesize a large class of borophosphate compounds, which are called helical borophosphates. So as you would see, they look hexagonal bipyramid in morphologically, and they have a very nice structure. You could see that this boron and phosphate tetrahedra are connected together in a wound round left or right-handed helix, which is the crystallographic axis. And then we have water channels inside this kind of chains. Okay, if you look at very carefully, you would see that they're also very much similar to the structure of DNA, where DNA has a double strand structure. However, these are not biologically motivated, so I would just show you the whole structure. So this, you have your same architecture, let's say helical ribbons, and they're connected to your metal octahedra, and you also have some kind of alkaline or alkali alkali metals situated around the structure. As a whole, the structure looks like a dense dot structure. You could see these are the borophosphate chains, and these are the metals which are kept around. But nevertheless, we could say that we can make this kind of structure very easily via hydrothermal synthesis. So we started off with cobalt borophosphates, and this is the XRD pattern, which means these are this reflection which shows that our material is phase pure, which is compared with the theoretical pattern, and we have a phase pure for both lithium containing helical borophosphates as well as sodium containing helical borophosphates. Okay, then we check the morphology of the material. This is the optical microscopic picture. As you could see, they are nice pinkish hexagonal bipyramids. They also, and this is the scanning electron microscope, where you could see even at the point, let's say 0.5 millimeter sized hexagonal bipyramids. And interestingly, if you zoom in here, you would see that they have pores. This is the high resolution image, and you could see that you have a pore size of almost 1400 nanometer. Okay, as I told you before, we deposited this, how to deposit this material on the electrode. So we took this material, we put it on in some beaker with acetone and iodine. We made this material get deposited on FTO glass and nickel foam. And now, as you see that this is the cyclic voltammetry of such a material. This is the thermodynamic potential for oxygen evolution reaction, and here, which is at 1.23 volt. And if you put, or if you apply the potential from this direction, you would see that you have oxygen evolution at around this particular area. Similarly, if you take nickel from this is even faster, you attain much more current than FTO, because this is much more conducting. What is important, I told you, is the O potential. So how much extra potential one needs to apply, so which is also determined by the by these curves. You could see that we need almost 290 millivolt extra potential to have oxygen evolution reaction. On the other hand, we can we need only 200 millivolt, which is very less compared to other catalysts reported in literature. So we also check or compare this curves with the reference materials such as iridium and ruthenium, which are supposed to be the best catalysts to drive this reaction. We also did some other uh, important compounds, and we see that our materials are much more active than all these reported materials. Same situation here, we get much better current and much better O potentials. As I said, it's also important to have better stability. What you would see here that they are stable for 24 hours. Some, for example, in the case of sodium, which is decreasing a bit, but you still see a very nice trend for all these catalysts as they are very much stable. So this is one half of the reaction where we produce oxygen. The other half is to produce hydrogen. So we also check the LSV, which means linear scanning voltammetry, which is very similar to CV, but you don't cycle, which we did in also alkaline solution. And you see that we have a very nice hydrogen evolution reaction. These curves indicate that we have hydrogen evolution. And we can also determine the O potential. We have almost 240 millivolt of O potential, and here it's almost 100. Just remember that the thermodynamic potential for hydrogen evolution is 0. So we need almost 100 extra potential here and almost 240 extra potential here to drive the reaction. So again, we compared our material with other known materials, and we see that these materials are much more active, not as good as platinum, because platinum is an excellent catalyst for hydrogen evolution reaction. It is very difficult to come even closer to platinum catalyst, but as I said, one of the other ways is to enhance the performance of the oxygen evolution reaction so that we can drive this reaction more efficiently. Again, we conducted stability, and as you see that they are very stable. So there's no problem with the stability. In the beginning, I told you that it's important to know if the catalyst remains or is it a real catalyst for that matter. So we try to look at the different microscopy or different analytics. So one of the pictures which I'm showing you here from transmission electron microscopy, this is the after a very short time exposure to oxygen evolution reaction, and this is after a long time. And what you could see here, this is the reflection obtained from electron diffraction. This is nothing but this says that the material is crystalline, and if you have no spots here, that means the material is amorphous. And what you see that this area here is crystalline, but the surface changes. So this means that we have a large change at the surface, which is forming amorphous shell. So our catalyst is not a real catalyst, but it's a pre-catalyst. So now we have to know what is the structure of this catalyst. So similarly, we also found out that in the case of hydrogen evolution reaction, they don't change much to a great extent. But what you could see is that they are surface passivated. There is some change on the surface of the catalyst, and also they remain crystalline, as shown by the intense spots of electron diffraction pattern. Okay, so now, as I said, we wanted to know the whole structure of the catalyst, which technically we could do by X-ray absorption spectroscopy. Those who do not know what is X-ray absorption spectroscopy, I would like to give a simple basic idea. So if you excite, or when your X-ray energies are enough to excite the core electron of the material to the unoccupied state, then you get a sudden jump in the spectrum, which is energy versus the intensity, and you see a just immediate jump. So this portion would give you the oxidation state and the electronic structure of the elements. But your electron is excited when you provide extra energy and you kick out the electron from your core level to the continuum, then this electron would interact with all the other atoms and provide you a pattern which is called X-ray absorption fine structure, which is this region, and which would give you a local a coordination number and atomic structure. This is very basic, but what you get something like this curves. It is nothing but the oxidation state. So this is our material, which was like this. This means we had oxidation state of 2+ in our powder, which is structurally all right. And then you take this material into oxygen elution reaction, and the oxidation state increases from 2 to 2.43. That means something happened to your catalyst and the surface changed. Similarly, in the hydrogen elution case, you had your oxidation state +2, and then after your catalysis, you decreased your oxidation state to 1.18. That means your cobalt, what you had in your material, got reduced, and here the cobalt is oxidized. This is done for cobalt KH, so we can only get information of the cobalt, information in cobalt sites. Okay, this again looks complicated, but you don't have to worry about it. What exactly it says is that, so we had a structure with particular composition, and after oxidation or oxygen elution reaction, the structure changed to a different structure. Similarly, in the case of hydrogen elution, it also changed to different structure. So we also compared with the cobalt metal, which is exactly matches after hydrogen elution, and also we use for the cobalt oxyhydroxide, which also somehow matches with the structure of after oxygen elution reaction. Okay, to cut the story short, what do you have? Once you have your structure, you really retain 63% in the case of oxygen elution reaction, and 83 to 49%, let's say 49%, your structure is retained, but rest changed on the surface. That means you don't have a stable catalyst, which exactly that changes significantly during your catalysis. Okay, so to show you what we learned from it, so we have prepared a cobalt borophosphate, including, which is typically I show it for lithium, and it changes immediately. We apply the potential to produce oxygen elution reaction, forming this material hydroxide, oxyhydroxide oxide on top of cobalt borophosphate. Similarly, if you apply negative potential, what you're gaining is metallic cobalt on the surface with some amount of cobalt oxide. On top of it, lithium cobalt borophosphate. Okay, so since we understood what's going on, so we just took this as an example, and we constructed an electrolyzer. So as you could see, this is this determines how efficient is your water electrolyzer. So this we could run it for 2.5 months without any problem. We had a very stable and high current, so this is very nice. So this is the picture how it was assembled, and this is the amount of hydrogen and oxygen produced. Note that hydrogen is always double than oxygen, just because you know that you are producing double amount of hydrogen in water. Okay, so let me show you the electrolyzer. What you're producing here is hydrogen, and what you're producing here is oxygen. You could see that hydrogen elution is always faster because it's double the amount you're producing, and you can also see some smoke, or let's say vapors or smoke, or you can see that these are the gases which is collected on the top. Okay, so now we know that we could really construct an electrolyzer. So we did this extended study to some other materials, which is a manganese based material, and we could achieve the durability of almost 5 months. So this means we can use this kind of catalyst or materials for catalytic purposes, not only for water splitting, for different other energy purposes. They're easy to make, easy to scale, they're stable. We understood the structure, we know what's going on here, and they are long-lasting catalysts. Okay, I think I have, if I have sufficient time to show you one more example, which is called intermetallic compound. This is a very hot area which is started very recently. So again, I think in your chemistry classes you always learn about alloys. So you have metal A or metal B with the same crystal structure and same atomic size. If you combine them, you form substitutional alloys. But if you take a metal C with slightly different structure and different atomic radius, you could either put them as an interstitial between those metals to form interstitial compounds, or what you can do is that you can combine them and they form a very ordered compound. They are called intermetallic compounds. They're very different from alloys because they're unordered, and they have a completely different electronic, physical, and chemical properties than that of intermetallic compounds. Okay, the intermetallic compounds are very complex, crystallographically very interesting, and of course they have very different electronic properties. Often they have used in superconductivity, ferromagnetism, thermoelectricity, and many different applications, including catalysis. However, the geometric and electronic influence of these materials have not been well investigated for energy conversion and storage. Why so? Problem is these materials can only be made by a very high temperature methods. That means you're forming very large aggregates with very low surface area, which is quite opposite what we need for electrocatalysis. And the problem also is that when you prepare such a material, you're forming let's say impurity phases, because you're using very high temperature. You have somehow no control on the complete reaction. The other solution for this problem would be that using a low temperature technique, maybe a solution based one. When we can make nanostructures, it would be great. That could compensate our desired properties, what you require for electrocatalysis, such as a high surface area. And also by doing so, we can also precisely control the composition and the element dispersity. Okay, we did this in a very simple way. We wanted to prepare a cobalt stannite because it is known in the literature that it's a very conductive material. And we took a very simple solution of cobalt chloride and tin chloride. We added polyethylene glycol as a capping agent in ethylene glycol, which has a quite high boiling point, which is almost 170 degrees. We reflexed and we added this particular sodium borohydride to reduce these metals. So there is a reduction in metals. So what happens? The first cobalt is reduced to cobalt 0 and tin is reduced to tin 0. And they slowly diffuse through each other through a Kirkendall effect, and then you form something like a cobalt in 2, which is tetragonal in structure. Okay, again, I don't want to make it more complicated for you. This has a complex structure. Just remember that they are, each cobalt atom here are surrounded by 18 atoms, forming a quadratic antiprism, and the antiprisms are again connected via edges to form a three-dimensional network. This is very important for us if you want to know the structure-activity relationship. However, at this point of time, we just leave it. This is again the X-ray diffraction pattern, which is very important to see whether we have made a pure phase. And what we see is that we have made a pure phase, and you see that it's a very weak diffraction pattern. That means you have a nanocrystalline material. So these materials, we looked into transmission electron microscopy, and we saw also from scanning electron microscopy, what we see is that they're very small nanoparticles and have made something like net structure. And we get some rings in the selected area electron diffraction pattern. This ring is nothing but we have formed nanoparticles of very small size. Okay. I show you these X-ray photoelectron spectroscopy. This is nothing but to check the oxidation state of the material, and the signal or the peak what you get around this area is relevant for cobalt oxidation state of 0, what we produced. And then we also get something like cobalt 2+. This is because these materials are very reactive. So sometimes they react with air and form a very small surface layer. That's why your material is getting oxidized. No problem here. Similarly, we get cobalt 0 and slightly oxidized phase. When we know that we made this material in a nanocrystalline form, we immediately deposited this on different substrate. Here I show you something on nickel form substrate in alkaline solution, which is 1 molar KOH. And what we again see this oxygen evolution reaction, we also compare this reaction with different other references, and we gain a lot of over potential, which is even at high current densities. And also we also check the hydrogen evolution reaction, and what also it is clear from here that we have better over potential. This is the O potential 230 and 95, which is quite good compared to the literature reports. And stability, as you could see, if you take only tin and only cobalt, they are poor. But if you make cobalt tin, they are excellent. They are at least for 14 hours. They could survive without any problem. And we have investigated even further, but I'm not showing you the complete pattern here, or the complete curve here. So as I said again, I will tell you again why it's important to understand the active structure of the materials. Interestingly here, what you see, you start with a nanomaterial, and after oxygen evolution reaction, you're completely forming an amorphous structure, as you could see from this pattern, right? No spots. But in the case of hydrogen evolution reaction, if you look into it after the reaction, what you see is still spots, which means that the material is not changed so much. Okay, we also investigated this by X-ray photoelectron spectroscopy. And again, it's not a surprise that if you take oxygen evolution reaction, your material oxidizes completely to 3+, which is needed to drive the oxygen evolution reaction. And in the case of hydrogen evolution reaction, didn't change much. Only what you see is the oxidation peak, which is responsible for surface passivation. Same situation here. You preserve your tin, and also in the case of HER, you have a very nice peak for your tin 0. That means your material didn't change much. You can also look into oxygen spectra. This tells you what kind of bonding situation you have with oxygen, which we have cobalt oxide bonding, some kind of oxo hydroxide here, and also some adsorbed water, which I think formed in case of both OER or oxygen evolution or even hydrogen evolution. Okay, we were interested to make, of course, the alkaline electrolyzer with this. So this is the schematic diagram, how they are constructed, and this is the potential what we show, which is very good. And the stability is, of course, very nice. As you could see, this is at 10 milliamp per centimeter square, which is a standard process to determine the efficiency to 10% solar to fuel efficiency, which is used for solar cells. And we have also conducted this experiment at even higher current densities for over 4 days, and they are quite stable. If you're interested, always you can construct some kind of alkaline electrolyzers in your own laboratory. So this is something like a pressure cell. You can connect your electrodes to the potentiostat, and you can apply potential, and you could see that this when the gases are releasing, because the pressure they are decreased, the water level comes, or the electrolyte goes up here, and then you have this difference in gases, so that you see that if you are 8 ml of hydrogen, you always get 4 ml of oxygen. So this means our efficiency is almost close to 100%. To show you a complete overview, so we started with the cobalt tin, and we formed a cobalt tin 2 structure with controlling the composition. And what we show is during oxygen evolution reaction, the catalyst doesn't remain constant or doesn't remain stable. It completely goes under reconstruction to form such type of cobalt oxide structure, or cobalt tin 2, which is remain in a very small amount, whereas in the case of hydrogen evolution reaction, this is almost stable. Okay, I think I do not have time to show you more data, but I would just show you that we also measured some manganese Galli structure, which also has beautiful structures crystallographically. It is very interesting, where each manganese is centered via 8G A8, that is gallium 8 units, and packed 3D network. This is a nice mapping picture. You could see the dispersibility of these both elements in the spectra. Again, usual characterizations are XRD and TEM. This all means that what we made is a completely pure compound with oxidation state of close to 0 for manganese and 0 for gallite. So this is an intermetallic compound, so we expect the oxidation state to be close to 0. So we also did some kind of oxygen evolution reaction. Same story. We get much better in comparison to other materials, and they also oxidize in case of oxygen evolution reaction. Stability could be done for 24 hours or even over 5 days, which is we can demonstrate at very low O potential, which is very good for lab scale. Again, we looked into the structure, what happens after, and we saw that gallium is completely leaching out of the structure, and what you form is completely more or less manganese oxides. So this is also can be shown in TEM or transmission electron microscopy. So these are the fringes which you could see if you from the high resolution spectra. This means that this is the lattice fringes, which can be directly correlated to the reflections of your XRD pattern. And they form three different types of structures. So from one, we start with the manganese galide. At the end, you are forming a mixed material with delta MnO2, beta MnOH, and alpha Mn3O4. We also did other catalytic, other characterization measurement, XRD, IR, also the extraneous and other extraneous for gallium. In each cases, the message was the same, that material is not stable under these conditions. So again, to show you how does it look like, so you start with a very nice structure, and at the end you are forming an active structure which is composed of these three: manganese oxide, Mn3O4, delta MnO2, and beta MnOH. And we also could identify how the whole reaction mechanism goes through. So it first forms this particular phase, and then it goes to this phase, and finally it ends up in this phase. So, of course, not only we can do water splitting, we can also do some more reactions because you are using electrolytic cell. If you separate those cells, we can also do some organic oxidation. I will not explain you anything on that, but what I can show you that apart from doing auto oxidation at one cell, which is anodic, you can also use some kind of very important precursor, which is HMF, we call it. So 5-hydroxymethyl furfural, which is a good precursor to degrade to form such kind of FDCA, 2,5-furan dicarboxylic acid, which is an important precursor for polymer industries. So by using one particular catalyst, and you can change the structure, and you can use it for two different reactions, which are highly challenging reactions, which I already told you. This reaction is very demanding in compared to hydrogen evolution, because this reaction determines how the efficiency of hydrogen could rise. Okay, so yeah, of course, this cannot be done without acknowledging people who have worked. So this is my group. So I have these are the people postdocs which are contributed. Kastian, Indranil, and Vijay. So these are the PhD students who this guy already finished recently. And there are some more coming to the group, and some are former members who also have contributed to our work. And these are the collaborators in and around Berlin. But there are many other collaborators which are all around the world, which I'm not mentioning now. Maybe important message for the students: if you are doing your masters in India, for example, we have plenty of PhD positions are available time to time. You could look at this websites here. So this is a very nice program, Big NSC. This is for the graduate students. So we have different PhD positions available. This is the call for every year. You could apply based on chemistry, biology, physics, and chemical engineering. Please look at this site and check what's relevant for you and apply to the concerned persons, or apply to, you send your CVs and with all the documents. So we also have positions for time to time the positions are available in something called BestCat. This is a combination of BASF, the company, and the catalytic lab in Berlin. So one could also get some PhD positions if they're interested towards industrial applications. And I'm also heading the group in Hazebe, so I will also advertise some of the PhD positions, but we also have plenty of PhD positions available for different energy applications. Please have a look. So with that, I end my talk. Thank you very much for listening.
Thank you, sir. The section was very informative. My team and I are so lucky to have you as a resource person in our webinar. Your presence and experience gave more meaning to it. Thank you, sir.
Welcome.
Are there any doubts or questions?
Are there any questions or comments? Actually, I was interested to see the photocatalytic unit you use in lab to simulate sunlight. Am I audible?
Yeah. No, I can.
Am I
It's
audible?
break.
Yeah.
Yeah, it's
Yeah.
breaking, but yeah, I can fairly hear you a little bit. Yeah.
Okay. So what that instrument which you use in your lab for photocatalyst for for simulating sunlight.
Mhm. Okay, so I
Yeah,
think I
in one
don't.
of the slides, use.
This is what I have is maybe the video, I think, right? Or
Yeah. Yes.
okay, so you want, okay, so I can, okay, wait a second. I can show you the video again. So this is the reactor which one could use. Okay, 1 second, maybe. Okay, I think here, yeah. I can show you this
Yes.
again.
That is actually
So,
very
so
interesting. It's
um,
yeah.
So what you could see is that this is a reactor, but you have to remember that when it's a simulated sunlight. It's not the real sunlight, which is approximately the same sunlight what you use if you go out. Or yeah, but what is important is that this reactor should contain a water jacket. So this should be consistently cooled down, or let's say kept constant temperature at probably room temperature, because with this intense light, the water can boil, and which already mediates the hydrogen production as well. So one should remember that. So this is a very simple reactor. You don't have to make any fancy reactor for this. You just have to have one neck, or maybe three neck, because two for the water jackets, one for the collection of hydrogen. That's enough. And we have actually this is the setup to show public, of course, to the students, but we also have different complicated setups which I'm not showing you here. So we can illuminate light from the bottom as well as from the top, and we can increase the efficiency by doing so, because you are stirring the solution all the time. So you want your material to have maximum exposure towards sunlight. So this is very important. That's why we, for the demonstration purpose, this could be very nice to show how exactly the whole thing works. But for a real situation of, for example, to collect more hydrogen, we have a different let's say reactors, which probably I will not be able to show here because I don't have it here at the moment.
Yeah, this is it's really inspiring for the students to see that such things can be made in the lab as a first step, and then we can go for the application level. And as far as I understand, you have made research, many more research in Boro Phosphates, right?
Yes,
And
you remember.
yeah, I remember. Yeah, so borophosphates have very good applications. And then going to intermetallic compounds, you showed an SCM image that after the catalytic activity, it has changed to amorphous to crystalline. So does that mean that the catalyst is still active, or
Yeah,
it can be
yes,
used further? Oh, okay, so
exactly.
it is still active and it is
Exactly. So
reusable.
it's a very interesting question. Actually, what happens is that you take a catalyst here, and so you want it to be, so if it's not changing, for example, when you start your highly oxidizing condition, for example, this is what I showed you in oxidizing condition. So you put a potential, yeah, and then you oxidize water. So the problem is, before oxidizing water, you naturally oxidize your material also, because the oxidation of the metal comes much before the oxidation of water. Yeah. So when you start, for example, manganese, yeah. So manganese, I took manganese, for example, manganese 0. The potential where the manganese oxidizes is the potential at 1.35, yeah, one versus reversible hydrogen electrode. But the water oxidation happens at around 1.55 volt, yeah. And then first you oxidize your material, then you oxidize water. So once you oxidize your material, it already changes, because in this case of gallium, for example, the gallium comes out because it's not stable, because when you oxidize something at these harsh conditions, you lose some of the other metals, such as gallium, and you already form a completely crystalline structure, which is like in this case, we got 3 different crystalline structures. But those are the crystalline structures which are stable at that particular conditions. They will not change further. They will stay as it is for a very long time. This is the problem in most of the catalysts, because what you start with is not your real catalyst, which is as textbook defines. Yeah, so it's constantly changing, and what you define is at the end is completely a different phase. And that's why we use in-situ spectroscopy. That means we monitor the change in catalysis during the reaction. We do it via X-ray absorption spectroscopy, which I showed you, or let's say EPR spectroscopy or different spectroscopies. We use a cell where we can monitor what's going on, exactly how the intermediate looks like, because it always goes through an intermediate step. You start with something, it goes somewhere else, and then finally you have something which is stable. So there is a start and there is an end, and then it remains stable. But of course, there are some examples as well that after getting or attaining the stable phase, it can also degrade. Yeah, because it can something can happen in the or something can happen within the structure that can also degrade the whole catalyst. But mostly, once reaching their optimum active structure, they remain stable.
Thank you. Are there any questions from the students or teachers? So this is indeed a new field for us, even though we learn catalysis in basic chemistry classes. But this was really interesting that catalysts have many advanced uses like this.
Yes.
Catalyst, electrocatalyst, and there are innumerable uses for this.
Correct.
So I'm
And
very happy that at least my students have some.
Yes, I also encourage students to in fact look towards application oriented fields. For example, now many countries in Europe or America, they are going towards green technology. Yeah, so this is one of the most important part, that people are trying to produce hydrogen, or especially electrochemical energy conversion. These fields are now hot, and this is booming fields one should consider. I think if you guys are really interested in pursuing your PhD, and then you should think about, there are plenty of opportunities when one could come and apply for this. I don't know whether, Anu, do you have master's courses also, or only bachelor courses in BCM?
No, we have only bachelor courses.
Okay. I think it's also a good idea when you start your, in fact, for bachelors also, you could apply in certain places to do your bachelor's project as well. And then, you can try to enlighten yourself and try to make this research, towards sustainability, for example. So, yeah.
Yeah, okay, so we are running short of time. So anyway, so I think there are no more questions. And thank you, Dr. Prashant, for accepting our invitation readily. Myself, my colleagues, and my college and whole management principal, we are really grateful for spending time for almost an hour. Thank you, Prashant. And I must tell my students that Dr. Prashant was a great source of inspiration and help to me during my PhD days. We were doing PhD under the same professor, but in different groups. And he was doing research in Boro Phosphates, and I'm really, really happy that he has actually continued in this field. And now he has 3 patents, and he's a very famous research group leader in TU Berlin. Thank you, Prashant. So
Thank
over
you,
to you, Amulya.
Now I invite Ms. Arati Prakash for delivering vote of thanks.
Good afternoon, everyone, to the one and all present here, Honorable Chief Guest and Resource Person, Dr. Prashant Wilfred Meneses, respected teachers, and all the participants. It is such an honor for me to get the opportunity to thank you all dignitaries. On behalf of Chemistry Department, BCM College, I would like to express my gratitude to all esteemed delegates of this international webinar for their presence and contribution to make this international webinar a great success. First of all, I would like to express my gratitude to our Honorable Chief Guest and Resource Person, Dr. Prashant Wilfred Menses, Group Leader, Technical University, Berlin, Germany, to take out time from his busy schedule to grace this international webinar with his extremely relevant talk on New Generation Catalyst for Water Splitting as part of our international webinar series Vykhari 2021. Thank you, sir, for your valuable words. We are really enlightened with your presence and knowledge. I am grateful for our college management, Principal Dr. Steffi Thomas, College Bursar Reverend Father Philmon Kalatara, for allowing us to conduct this international webinar. I would also like to thank our beloved HOD Dr. Anu Thomas and JC Miss, Meenu Miss, Anisha Miss for organizing such an international webinar and their immense support to make this webinar a great success. And also, I would like to thank the organizing team, volunteers, and all the participants who have gathered here. Once again, thank you everyone for making this international webinar a great success. Thank you.